Wonderful. I think we have got a good answer here. The ruler support has got 95 and the hinge support has got 130 kilonewtons, and the horizontal force, the horizontal reaction is 0. That is the correct answer. Thank you very much indeed. And that is from Vin. I will write the name down to keep a record of the contributions. So I have here a record of anyone who is contributing to the session. So that is Vin. And I will also keep a record of the chat box. So I will copy the chat box there, and then I will keep a record. Okay, so you are obviously very good in this kind of thing, but let me just try to add a little bit more value to what you already know, if possible. So the question you've been thinking about is this one here. So if you are not confident yet, very quickly. Of course, these kind of solutions are very quick. They were done in front of the students a long time ago. So first you give indication of the name of the points, and then you have a rule of support. You must indicate first the direction of the reaction. You assume it's going up, perpendicular to the movement. So the movement is horizontal movement, so the reaction must be perpendicular to the movement. If the rule of support was inclined like this, the reaction must be perpendicular to the movement. And then you have here a hinge or a pin. So you can develop two reactions. One vertical, again you indicate the direction, and one horizontal, and you indicate the assumed direction, assumed. Of course, we call up positive and to the right positive, but as I said before, I like you to think about it from engineering point of view, directions, and what's going on physically as well. So that is obvious, there is no horizontal action, so there is no horizontal reaction. And then you take rotational equilibrium. That's what I call sigma moment at any point, as I mentioned before, must be equal to 0. So I'm taking rotational equilibrium about this point because I want to cancel out this reaction, because this reaction is going through B. So the moment of this force around B is 0 because the distance is 0. This is the only reason why I went to this point and established the rotational equilibrium around B. And that must be equal to 0. The sum of all moments, all forces must be equal to 0. Around any point, actually, any point in the plane of the forces up to infinity in all directions. So VA times 10 going in the clockwise must be balanced by 25, first the UDL, 20 times 10 times 5, because the resultant of the UDL is in the middle, and the value of the resultant is 20 times 10, and the arm is 5, so 20 times 10 times 5, plus 25 times 1, 25 times 1. So basically, you're trying to balance what is going clockwise with what's going in the counterclockwise or anti-clockwise, or American accent anti-clockwise. Okay. So from here you get here, and then you can actually do it this way as well, which I prefer. Now I'm taking or examining the rotational equilibrium about point A, location A. So rotational equilibrium about point A, what is going counterclockwise must be equal to what's going clockwise. So when I take moment around A, BA and HA will not appear because they are going through this point. So the arm of these forces are equal to 0 about this point. So what is remaining is BB times 10, but added to it in the same sense, in the same direction, and counterclockwise is a 25 times 2. So BB times 10 plus 25 times 2 must be balanced by 20 times 10 times 5. Yeah? And then you get BB. This step here, I like to emphasize, you must always check your solution. So now I didn't use the vertical equilibrium to find the vertical reaction, so now I check the vertical equilibrium. So what is going down must be equal to what's going up. So what is going down, 20 times 10 plus 25, and what's going up, the two reactions, two vertical reactions, also 130 plus 95, so must be equal. So this step seems to be missing from many calculations I've seen before. So please always, as engineers, try to develop the skill of checking your answer. Yeah? So thank you very much for that. And another way you can add your knowledge, or you can add your ability using your variables. So this is actually a principle which you probably did already, which is the principle of adding effects. So this can happen when the material is still elastic. Elastic material, so we can add the effect. So first, we consider the model alone, without the 25. And that's very easy because the result of the union is 200 kilonewtons per click, of course, 100 and 100. Wonderful. And then we add addition now. This principle is very important in analysis. We are going to use it to analyze very complex systems later on, statistically indeterminate systems. So we can add now the effect of the 25 alone. So the same system, but only 25 acting on it. And now if I want to balance the 25, how do I balance it? Of course, if you want to balance the system around this point, you have 25 times 2 rotational effect around A if you like, and that's 50 kilonewtons. So we must have a balancing moment of 50 kilonewtons going in the clockwise direction. So going in the anti-clockwise direction must be balanced by rotational effect going in the clockwise direction around any point, but we are choosing point A, again to eliminate the reactions which we don't know yet, by the way. So to balance this rotational effect from the 25 around point A, 25 times 50, so the vertical reaction here must be going down, and it must be 50 over 10, which is 5, because 5 times 10 will be 50, 25 times 2 is 50 in the opposite direction, so the system is balanced around this point here, and it's indeed now will be balanced around any point once you calculate the vertical reaction here. So the vertical reaction here will obviously be 25 plus 5, 30. And have a look. 100. Sorry, what happened? Doing a bit math. Sorry about that. So what is happening here, as you can see, very easily. Now, 100 up, 5 down, 95. 100 up, 30 up, 130. So this is just a kind of an idea to help you to check and to think about the system in a different way or in a practical way, or like to develop a skill of feeling. We're hearing about calculations, but also about how you appreciate the system and how you understand the system. Okay, so now we are going very quickly to revise. For some reason, my screen is a bit jumpy. Maybe I need to come out and come in again. So now we need, excuse me, maybe I need to switch. I need to come out and come in again in this kind of notes. Sorry. By the way, can you hear okay, and you can see okay so far? Okay, wonderful. Yes, you can write in the chat box. Great. Thank you very much indeed. So let me just load the notes again. So hopefully now it will be better. So maybe not. So the other two questions we are going to work on are these last two questions, please. Again, they are very easy for you, but again, I like your feeling, how forces and so on. So again, please, would you like to calculate for me the reactions for this frame? We are going to study many of these frames later on. And these frames actually are very much used in the industry. And you have rigid joints. These joints are designed to be rigid, strong joints, so they can transfer bending. Otherwise, this frame will collapse if the joints are weak, joint C and joint E. But yeah, please calculate the reactions again, maybe 5 minutes, and then type your answers in the chat box. And I'd like to see many of you typing the answers in the chat box, please. So yeah, over to you. Thank you.
So write your answers in the chat box when you're ready, please. Thank you. Oh, you've already written some answers here, and that is again my pronunciation is not very good, but that is teen. Thank you very much. And let's go and revise this quickly for everyone. So again, you can think about it as two components, but very simple. That's what I do, and that's what you do. Forces in the x direction. First, before you do that, you must indicate. And the first step, actually, some of my students actually don't do this step very clearly. Excuse me. And then they get very confused later on. So before you do anything, indicate the correct reactions according to the nature of the support. And then establish translation equilibrium in the x. Okay, and then here I did rotational equilibrium about A, and then rotational equilibrium about B, and then I use sigma y, sigma fy to check my answer. So you can do this, and that's really a good practice. And as you can see here, if I'm taking equilibrium about A, I have VB times 6 going in the clockwise direction. In the counterclockwise direction, you have 40 times 3 plus 10 times 6, and you get VB of 30. So here's 30. And it makes sense. And always ask yourself, does this make sense? Because you are pressing here, so you are putting more pressure on B. And you're trying to lift support A up if you are pressing horizontally. So it makes sense VB will be greater than half the 40 if you have a force going this way. That makes sense. And then if you take rotational equilibrium about B, so you have VA and the 20 going in the counterclockwise direction, V times 6 plus 10 times 6, and in the clockwise direction is the 40 times 3, and then you get V is 10. Okay? And then you check the sum of the forces going up must be going, some of the forces coming down, or the other way around. Of course, as you increase this horizontal force, VA will decrease, and at some stage it will get to 0, and then it will reverse and it will go down after that. So if it is 20 kilonewtons, what will happen? 20 times 6 will be equal to 40 times 3. So if it is 20, the reaction here will be 0, correct? You agree? And then the reaction here will be 40, yeah? So please think about it in this way as well. Try to investigate the behavior, change things, and experiment and find out what is going on. So yes, so that is a good practice as engineers. Okay, so the final one is this, not final one, but the another task here for you to do quickly today. I know this information is very basic for you, but you must have the basics to move on because otherwise life will be complicated if you move on and you still need some kind of additional knowledge in calculating reactions. So this one, please. So please let me know if you put any values in the chat box because I cannot see actually the chat box from this screen here in front of you. So has anyone got any answers for me, please? Excuse me. Wonderful. Great. Yeah. Great. Wonderful. I will make a record of the chat box later, as I said, but maybe I'll put down the names. So Tina, I think that's twice, and I'm not sure how to say the name. Is it Kome? Is it Kome White Shiga? Which Shiga?
Yes, yes.
Kome Wichiga. Thank you, Kome. Merci. And also Min. Excuse me, my voice is really not good today. I'm a bit sick, as I said, so my apology for that. So they all kind of similar answers, as they are correct answers, of course. You're very good. But please, as I said, develop the ability to check. There. So here, again, very quick calculation, very easy calculation. And again, moment twice and checking by the sum of vertical forces must be equal to 0. So again, we have a UDL resultant. UDL resultant, 20 times 13, of course. And the location of the UDL resultant, it's okay when you are calculating reactions to replace the UDL by its resultant. But when you are calculating bending moments later on, you cannot do that really. And I'll explain why when we revise the bending moment diagrams and shear force diagrams and so on. So, but when we calculate reactions, you can do that at least in your mind. And this is why also I indicated here the resultant in dashed line, because it doesn't really exist at this point. It is the equivalence of the UDL, if you like, the overall equivalence when you calculate reactions. But when you're calculating internal forces, you have to consider the intensity of the UDL wherever you are calculating the bending moment value. You have to take either to the left-hand side or to the right-hand side. But I'll explain all of this later on. But for now, it is okay to do that. And of course, the distance of the resultant to this support is 3.5, and of course to the other support is 6.5. That's fine. And then you have the rotational effect about A must be 0, and the rotational effect about B must be equal to 0. And in fact, as I said, rotational effect about any point in the plane of the forces up to infinity. And if you don't believe me, take any point somewhere here, assume distances, and take any point on the page you are working on, and work out the geometry, and take moments about this point, and the sum of moments must be equal to 0. So that is fact, because the entire plane is not rotating, cannot rotate. If the plane of forces has got any rotational effect, this beam is not in equilibrium, is not in rotational equilibrium. So the significance of A and B is basically because I want to eliminate the reactions once, so I can actually calculate directly VB, I calculate directly VA. Otherwise, VB and VA and HA will appear in the equations, which will make kind of extra work for me. This is the only reason why we do this, but I think you understand all of this. I just want to say it just in case someone still not clear about that. And you must include this step here, please. Checking. Check your answer. Very soon you'll be using computers, and I did this quite a lot in the UK with my students, simulating complex systems and so on. But actually, you need to have some idea about what you will be expecting coming out from the computer. So this is why you need now to think about what you're doing a little bit more in addition to carrying out the calculations correctly. Thank you very much for your contributions. And now I think we'll have a break and I'll get some a drink for my voice, and we'll meet again after 10 minutes, please. So so now, yeah, we'll come back at 10 o'clock. That's all right. Thank you. So, welcome back. So we will continue, please. Can you hear me? Can you still hear me? Please. Okay, thank you. So we'll continue. We'll give you additional examples to work on and see if you need more kind of support in this ability to calculate reactions. So I'm waiting for this Excel file to launch. It's here actually. Good. So these are very simple examples, but please make sure you are familiar with this kind of material. You can go back to textbooks and be very, very clear about reactions. And we've done something similar to that, so I don't think we need to look more at this. Maybe this one might include more interesting questions for you. And I am not sure about your background, whether you have done things like that or not yet. So this is a pin jointed structure. You call it trusses. So that is a truss, and we also call it truss. So this is truss. I'm trying to write on the screen, but for some reason it's not allowing me to. But that's fine. So that is a truss system, and perhaps you like to calculate for me the reactions here. Maybe you can do that now, actually. Why not? So can you do this for me, please? So this is a pin jointed structure, a truss, and you are required to calculate just the reactions. You've learned also how to calculate the internal forces, and that is also important, very important. So please calculate the reactions. Excuse me. So if you are used to the indication of a pin, so this is a pin jointed system. So all these joints are pin connections, pin jointed structure connections which allow free rotation, free rotation. And these supports, this is a hinge support or a pin support. This support is the same kind of support. But it is drawn to confuse you a little bit, inclined like this, but actually you will get the same kind of behavior. You have a vertical reaction and a horizontal reaction. So if it is a ruler support doing this, you have only one reaction perpendicular to the plane of movement. But if it is a hinge support, it will still give you two reactions, vertical and horizontal reaction. And the two values, they are not linked, if you like, to each other. Yeah, different from the ruler condition. And also here, actually, there is a possibility to develop a vertical reaction, of course, because this is a hinge. But the vertical reaction here has got a specific value, which I want you to confirm. And that is related to the fact that this is a pin joint. Maybe this is a little bit harder, but I'm sure you have the skill to calculate these reactions, please. Thank you. So the loading is W, vertical W at joint G, and 2W horizontally acting at D, at joint D. Excuse me. So we've got some answers from Teen. So let's have a look and see what is going on. But maybe I'll wait 1 more minute or 2 minutes for other colleagues to also give their opinion. So I'm waiting for more contribution in the chat box, and then I'll show you the solutions. So you can see the solutions in front of you anyway. And then you can check also your answers. So let's see who else managed to solve this problem. So we've got 3 students providing interesting answers here. So Vin has got a slightly different answer, and Tommy has got similar answer to Tim. So Tommy times 2, and Vin and Tim. Okay, thank you very much. So let's discuss a little bit now different solutions here. So let's have a look at the solutions. So we need to establish horizontal balance and vertical balance and rotational balance. So from the vertical balance, obvious VA must be W. Sorry, what I'm talking about. VH must be equal to W because you haven't got any other vertical forces. I will talk a bit more about what's going on here, but for now, we just accept that there is only horizontal reaction here. The vertical reaction must be equal to 0 as this hinge support. And I will ask you very soon why this must be the case. And this is related to the fact that there is a pin connection here, related to the fact that you have a pin connection and a pin connection here. So the force developed inside the member here is along the axis of this member, along the axis of this member, okay? And so that is clear. So this value is clear. So if we go back to the rotational balance, it will give you the horizontal force at A. So I'm taking moments about H. Take moment about H here. So if you take moments about H, you cancel out VH and HH. And about H here, you have moments going in the clockwise direction and moments in the counterclockwise direction. Actually, it's written here the other way around. So HA times 4 is the counterclockwise direction, HA times 4. And in the clockwise direction is W times 4 plus 2W times 4 as well. So the horizontal reaction at A must be equal to 3W. Now they have 3W going this way and only 2W going this way. So you must have W going this way. So HA must be equal to W going this way. So this was done actually by a research assistant, this calculation. So the sign might be a little bit confusing here, but it is actually designed in the spreadsheet. So but HA is as indicated, and it's equal to W. So this is W. This is, as we said, 3W in the directions indicated in front of you. And can anyone tell me then, please, why you cannot develop? Again, I explained, but you can repeat what I said if you like. Why you cannot develop a vertical reaction here. And I must add, when we analyze systems like that, we actually ignore the self-weight. So the self-weight is not considered, and that's something which confuses the students because they think, oh, there is a self-weight here, so I must have a vertical reaction here to support the self-weight. You are right, but in our analysis of these systems, we actually ignore the self-weight. And if I'm designing a building or a bridge and I'm using this system, I actually put the self-weight, excuse me, of this element, some of it here and some of it here. So I cannot allow any bending developing in these elements. Otherwise, it will confuse the analysis, you see. So can anyone talk to me and explain to me why you cannot develop a vertical reaction here at joint A? I explained it already. So what do you think? Oh, yes, there is a question in the chat box about this. Okay, yeah. So I was hoping you will be able to explain to me, but I will explain. Can anyone answer my question, please? And maybe you try to explain, and I will hear your voices and your explanation. Okay, so let's try to explain this a bit. Yes, yes, please. Yeah, go ahead, Vin. Yeah, Vin. Go ahead. Thank you very much for your contribution, Vin. But unfortunately, I cannot hear you very well. There's an issue with the mic on your side, but I think you are correct. But I'm sorry, I cannot hear very well. I'm sorry about that. Say it again. Your voice is not very clear. I'm sorry, but you can try again if you want. Your mic is not very clear. I'm really sorry about that. Uh, okay. Okay, I think you are on the correct understanding. So let's discuss a little bit more, and that is actually linked to the next topic. But let's talk a little bit more about it with you as well. And you can interrupt me and you can discuss. So let's have a look. So perhaps we go back here, and perhaps we take a cutting of this system. So let's snap this system here and put it here. And also go back here.
Sir, you didn't
Yes.
share your screen?
Yeah. Okay. Yeah, of course. Thank you. Sorry. So what I did, I'm trying to isolate the joints to explain this to you. So I took this joint here, and then I'm going to take the joint next to it. So first I took this part, and now I'm going to take the part next to it here. And I'm going to put it here. So this is a pin joint system. Can you all see this clearly, please? Oh, wonderful. So element AB can only develop an internal force along the axis of this element, can only develop axial force, okay? So let's represent the axial force by a different color, I guess, maybe by green for now, and maybe make it a bit big for you to see it, maybe this one here. So element AB is a horizontal element, and it can only develop a force along the axis. In this case, it will be tension. On this side, these are the internal forces. Yeah. So for a pin joint system, I need to establish the vertical equilibrium and the horizontal equilibrium. By the way, this is also going to be equal to 3H like VA. Sorry, like HA. It was 3H, wasn't it? Yeah. Now, for the horizontal equilibrium of joint A, that is clear. There is a horizontal equilibrium here. If you calculate the internal force, it must be equal to 3H, and we will do this next in the next topic. So the horizontal equilibrium is okay. Now have a look at the vertical equilibrium, please, because you must achieve at each joint, you must achieve, and by the way, this is the free body diagram or free body diagram, like in the UK, we say diagram. In America, they say diagram. This is a free body diagram of joint A. Have a look. If you assume there is a VA here, VA, and then you want to achieve the vertical equilibrium, what you will write? You write VA equals 0, because there isn't other forces acting at joint A. And the reason VA must be equal to 0, because this element here can develop only axial force, and this element here is horizontal. So if this element was not horizontal, so if AB was inclined like this, AB, then you will develop a vertical reaction. If this is pulling this way, so the vertical reaction will have to go down, but the vertical and horizontal reaction must be actually along the axis. They will be pointing, it will be pointing. This is the overall reaction, pointing this way. But in our case, member AB is a horizontal element, member. Therefore, the internal force is tensile force along the direction AB, and there is no vertical component acting here, so VA must be equal to 0. So if you wish, you can assume VA, which is logical, but then you have to investigate the equilibrium of this joint before you proceed, because of the fact that VA must be 0 to maintain the equilibrium of the pin joint at A. So I'll go back to the chat box and please confirm if you understood. So what do you think? Did you understand this explanation? Which will lead us actually to think about, maybe will help you then if you don't really get this idea. We will do pin jointed structures, pin jointed frames. So what do you think, please? You can type your comments in the chat box for me to have some idea of your level of understanding. Thank you. You can come back to me and ask more, and I will try to explain more. Okay, so I think I will, at this stage, if you feel you would like to think about it, that's fine. This is another question perhaps I will give you as homework, but I will wait maybe a couple of minutes for you to think about this and ask me if you like me to explain again or give you more examples. Or so does anyone like me to explain again, please? You can ask me.
Teacher, can you explain me again because I still get it clearly?
You didn't get it clearly. Okay.
Yes.
So yeah, okay. So that is, I think actually what might be the best in this case is to revise the next topic, and then things will become very clear to you, because I think the issue is related to something called pin jointed systems. So if you allow me, I will go to this. I've got a question in the chat box, and let me do this, and then I'll take more questions about this later on. So if you allow me, I think you need to revise this topic if you want to really understand what is going on. So let's revise a little bit, and then everything hopefully will become clear. So I assume you studied in engineering mechanics something called pin jointed structures or trusses. Pin jointed structures. So this is how they look like. Many bridges in many countries I've seen designed in this way. You can see here the elements connected in a specific way, and the loading is applied in a specific way. And then you carried out calculations related to such system. And you managed to achieve calculation of the magnitude and nature of member forces, and identify the nature of these forces even without calculations. You looked at something called ties and trusses, ties and struts. tension and compression. You looked at pin joints, pin connections, and the meaning of pin connections. You looked at the assumptions. This is, I think, why there's some confusion about the problem I tried to explain earlier, because it's very much related to this kind of systems, pin jointed systems. And this is a bit which is relevant to the solution I was just trying to explain to you. Calculation of internal forces in a pin jointed structure using the equilibrium of joints method. So if you want to understand more about this issue we were talking about, please revise this topic here, equilibrium of joints method. And the idea about determinacy and stability of pin jointed systems. So there is a equilibrium of joints method, and there is a section method for analyzing these systems. So the previous example highlighted to me, perhaps there are some issues related to your kind of understanding of this topic. So please revise, and we can revise as well together. So maybe we can start a little bit now. So this is the idea why joint A must have only, the joint we were talking about earlier, must have only horizontal reaction, because at joint A you must achieve the sum of forces horizontally must be equal to 0, and the sum of forces vertically must be equal to 0 at one specific joint A in the previous example. So this is why vertically there aren't any forces acting as a joint, so the sum of forces must be 0, so the vertical reaction at joint A must be 0, as simple as that. But anyway, so maybe to remind you what you've done before, can I ask you now, please, to calculate the internal forces, if you recall how to do it? I will give you this question here, which is actually has good similarity to the question we were asking before. But what I ask you to do first, please, is to calculate for me the internal force acting in member AB. Just one value for now. I'm not asking you about the reactions. Ignore the reactions for now. So can you please calculate for me the internal force in member AB? There is, a hinge support here and a hinge support here, and a 10 kilonewtons acting at joint B. Geometry is very simple, very easy, 2 and 2, vertically and horizontally. So the angle is 45 degrees, very easy. Over to you, please. What do you think the value of the internal force here? And do you think there is any shear or any bending, or what do you think is going on in the material of element AB, as according to the assumption of pin jointed systems? Over to you. 5 minutes at maximum, maybe. So my question is not about the reactions now, it's just about the internal force. And that will help me to answer your questions about the previous example, which some of you understood, maybe some of you didn't. It's okay. So that will help us to clarify our understanding. Okay, there's an opinion here in the chat box saying that there is no internal force on element AB, which is a okay kind of opinion. But if we think about the physics of the problem or the understanding of the problem, if you are pressing on and there's another solution saying the internal force is 7.07, and is it tension or compression, and is it axial or is it shear or is it bending, you know, but here you said kilonewton, so it's an axial force. But we'll have a look. So I think we need to revise, please, this topic. That's really important. So looking at the chat box as well, there is a from Tan asking about the vertical equilibrium VA plus VH must be equal to W. Yes, of course, it must. But you still you need to use the idea I explained to you. Otherwise, you have 4 reactions and you have only 3 equations of static equilibrium. So you need to have the additional information related to the pin joint, which I explained earlier. So let's have a look. Any other solutions, please? It's wonderful because I can see your thoughts. I can learn more about your abilities as well. So that's great for me. Thank you very much for contributing. And I will make a record anyway because any contribution is good contribution for me. I like any contribution, whether it is something which is accurate or not. It doesn't matter for me. It's engagement. I like engagement of the students. So Duke and Gia. Thank you. Any other opinions, please? Okay, so you have a task, homework to revise this topic. Because of course, we need now to think about what's going on inside the material. So we need to establish at least the mechanics of the system before we go deeper into the material. So this is an item for revision. Can I ask you, please, have you actually done this topic before, or this is the first time you hear about it? So can you answer me in the chat box? Have you already done trusses before in engineering mechanics or not? Ah, your first time. Okay. All right. So has anyone done pin jointed systems or trusses before, please? Anyone in the meeting? Because I know it's covered in engineering mechanics. And of course in structural mechanics, but you haven't done structural mechanics yet, I think. So you haven't done it before. Okay. So in that case, we should move on and we will teach you this topic in detail another time because it's a big topic and I've got the notes here available, but it will take a long time to cover basically. So I think we will move on to what you've done already and revise. And then when we meet in the classroom, we will do the analysis of systems which you haven't done before. So can you please, for the final time, can you tell me if you have studied this topic before anyone, I will be really grateful because that will help us to plan your sessions in the future. And I can ask, of course, Professor Ben. Well, I don't think he's in the meeting at the moment. But has anyone please studied pin jointed structures, trusses? So if I don't get any message in the chat box, I will assume you have not covered this topic. And then we will revise some topics. So, okay, no, you haven't. Okay, I'm surprised, but that is okay. Do not worry. So, we'll leave this now and we will revise what you have done. So, I'm sorry I was under the wrong impression. Okay, so you have done bending moments, I'm sure, bending moment values, but actually now it's time to have a break. But when you come back from the break, we will revise a little bit about bending moment diagrams, if that's okay. Yeah, and make sure we are all clear about calculations of bending moment value. Okay, so now it is 10:50. So we'll come back at 11 o'clock and we'll do a bit of revision about bending moments and shearing forces. Okay, thank you. So welcome back, and we will proceed a little bit and see what we can do. And then, of course, after the holidays, we'll continue with more explanations and more detailed kind of outline of these topics, and we will help you as much as we can to clarify all the issues you have. So let me also check your understanding, please, about this. So this is about bending moments, about internal forces. By the way, can you hear me? Can you hear me, please? Thank
Yeah.
you. Thank you. So now I want you to just, as I said, we will explain everything in detail. It's just I'm trying to get to know you and to get to know which areas I need to focus on. So now we are looking at something really, really important in engineering. The bending moments, these are the internal forces. I believe you have studied bending moments, and you've also looked at shearing forces. Is that correct? You have done this before? Can anyone confirm for me, please? Oh, there's something in the chat box. Oh, you haven't studied about bending moments before? Okay. Oh, you haven't done engineering mechanics. Oh, this is the issue. Okay, 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 okay. So what have you done so far? Have you done any mechanics at all or no mechanics? Ah, this is your first course. Oh, okay. My apologies. Okay, 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 okay. Excuse me. Okay. How about what is Comé coming from France? Have you done any of that? Comé, is he still here? Well, okay. So you haven't done any of that. So okay. So my apologies then for the misunderstanding. Um, so if you haven't done actually engineering mechanics, but you managed to calculate reactions very well, so that indicated to me. So where did you learn about calculating reactions? Actually, that's interesting. So if you have not done engineering mechanics, how did you learn about calculating reactions? Can anyone answer me? Uh, so you've done fundamental physics in the chat box, which from this you know how to calculate the reactions. Okay, okay, okay. So I understand now. So okay, I had the impression you've done engineering mechanics. So thank you very much for correcting me. So in that case, what we can do in that case is to expand a little bit on reactions, and then you can after the holidays we'll go through the material in detail about bending and about internal forces. So yes, okay. Thank you very much for clarifying this for me. So you have not done any of that, which is okay. So I will do this in detail in front of you after the holidays. So just to prepare you for that, so we are looking at like the bridges you have in Ho Chi Minh City and Vietnam, lovely bridges. You have elements like this, resting, supported by vertical columns. and then something is happening inside the material. So as the traffic goes over the bridge, the material will develop stresses inside, and we are trying to establish what kind of stresses, what is happening between the grains of the material. So the reactions, we've calculated reactions, and you know how to do reactions from fundamental physics, but maybe I should have actually explained in more details about reactions. So I will add to your knowledge after the holidays and when I'm not feeling so sick. So again, we will study about building systems and transfer of forces and behavior of different elements in the building, and how the load is applied and how the load is transferred from the floor. You are in your house, in your room. If you are on the ground floor or the first floor, the weight will go straight to the ground. But if you are on the second floor or whatever, the load will be traveling through the floor to support elements, and these elements here will transfer the load. The horizontal elements will transfer the load to the vertical elements, and all of this has got names. You can see the names here, might not be clear because the image is not very clear, but we will expand more and more on that. And then the load will be transferred to the ground. The same ideas in very impressive systems. This bridge in Hong Kong, the distance so the distance between this pylon and this pylon is 1,018 meters, over 1 kilometer. And the ideas are the same. We're trying to work out what are the internal forces in the system in terms of tension, compression, bending, something called shear, lots of things going on. And in the coming weeks after your holidays, we will look at all these forces and the stresses produced by these forces. So we will learn about bending, this word bending, which you haven't done before, bending moment. So we will learn in details about bending, and also about the previous topic I mentioned about axial stresses. So so we will build our knowledge from the beginning. So this material will be covered in details after the holiday. So this is a very simple idea. When you walk over a beam like this, or an element which is horizontal, supported here in a certain way, supported here in a certain way, this element will bend, will curve. There will be a curvature. And we will look at this kind of behavior, and we will look at what kind of stress. I don't know, do you know this word, stress? Of course, you know it in terms of people when they are stressed, but in terms of the material, maybe you've done this in physics as well. when you have something under tension, if you have an element, maybe you've done this, maybe you can confirm for me. If you have something like that, and then you apply a force to it like this, apply force to it like this. If the force is F, and if the cross-section area here is A, you've done this in physics, sigma, which is the stress, equals force divided by cross-section area. Has anyone done this? Sigma is the stress equals force divided by area. Anyone? I'm trying to learn about your previous knowledge. Anyone? No? Ah, like pressure. Okay, yeah, that's right. It's like pressure. Thank you very much, Ten. Like pressure. Okay, so you've done this concept. Fine, please. Okay, so I'm learning a little bit more, and I'll ask more, Professor Ben. Someone has got their mic on. Yeah, Kung, Tai, Quang, please put your mic.
Ủa anh dưới nhìn điệp điệp vậy? Gì thả chim ngoài vậy trời?
Can you please switch your mic off, Quang? Can you please switch your mic off? I don't have control here to switch your mic off. Okay, let's see if we can go here and switch the output. Anyway, so my apology for the noise coming from our colleague because he's listening to music. So that's fine. But anyway, so I will cover all of this after the holiday and teach you about all kind of things related to bending. So I think what will be best for us in this case is just to prepare you for what is coming. And I would like you please to make a note of all these problems and have the reactions ready for me. So now, I know now this is going to be for the next topic, but have these problems ready because we are going to add more and more information. So please make a note, take a screenshot or take an image of these problems, and I will leave this for you as homework to have it ready for me for next time I see you. So what is required from you is to make sure you have the reactions ready, and then we will continue in our course. So make a note, please. This question here, I know it's simple, but the first step of analysis will be calculating reactions, all of you. Especially now, I know you haven't done engineering mechanics, so and you need to submit your answers to Professor Ben, to your professor next week. You need to, sorry, not next week, after the holiday, you need to give your answer to all of these questions to Professor Ben in the session after the holiday. So please make a note of these questions and I will leave it with you. And then I will wish you a nice holiday after that. And then we can meet after the holiday and we'll explain everything in detail.
Thì không có lấy
So
hơn
this
cái
is
cái
another
trường
question. This is question number 2. Question number 2. Take a screenshot or take a snip like what I do. Click here like using this tool here, which you have in your computer. And you can do this and you can snip it like this and then take it to Word and copy it and take it to a Word file or whatever. And then you can solve these questions in your own time. So this is number 2, easy. Number 3, all of you please, because now I know that you need to really be confident in doing this. Otherwise you will struggle because you will have to build on all of these kind of systems
không thấy em có
and
lên mấy cái thìa để
information
em muốn
about
là
reactions. So please make a note of
gia đình thì có
question number
thìa á, nhiều
3.
có gia đình nữa.
Again,
Nhưng mà có cái con cặp đó là con
snip
Phước.
and so on.
Mà dám lấy đồ gia đình độ mà năm gia đình nó ngồi cái gì
Mr.
ngồi corridor á không
Hello.
không có phim gia đình luôn.
Excuse me, Professor.
So someone is going to call Wang, but meanwhile I've turned the volume down so I do not hear the music. But anyway.
Can I have 10 seconds to call him in Vietnamese?
Okay, yeah, I'll give you 10 seconds. Okay, thanks. Thank you very much.
Anh Phong ơi, anh Thái Quang Phong ơi. Anh Thái Quang Phong ơi.
Dạ ok, tôi nghe sao ạ?
Không có gì anh ơi, bọn em nhắc anh tắt mic tại nãy giờ ồn quá, ảnh hưởng tới lớp này.
Oh, thank you. That's okay. Thank you. Yeah. Okay. Thank you very much. So what I was saying, if anyone missed the instructions, you need to solve all these questions. You need to find the reactions and hand over to Professor Ben after the holiday, straight away after you come from the holiday. And please have very clear presentation. So your calculations must be very clear. And we will look at your solutions to make sure you can continue. Because I had a kind of a misunderstanding. I thought you've done this before, and I went through it quickly as a revision. But actually, you've done it, but not in detail. So that is question number 3. And you can see here I left space because we are going to add more and more calculations about this system, about what's going on inside the material. So the entire course, this strength of material, you haven't actually done this before, you don't know what that is, and we will go over reactions again. So that's number 4. Number 5, again, you have uniformly distributed load, like pressure. Someone said about pressure, but this is kilonewton per meter. So each meter has got 15 kilonewtons acting on it, like the idea of pressure. Oh, sorry, this here, the number here moves. This is number 5. So this is like the intensity of the pressure, but the pressure over an area, the UDL, is uniformly distributed over a length, 1 meter, 15 kilonewtons over 1 meter. So this is number 5. If you want me to put the problems again in front of you, I can, but you must submit the solutions to your professor when you come back from the holiday. So this is a cantilever system. Again, you might not have studied this in detail, but yeah, try. And again, if you feel you haven't really studied this kind of system before, make a note on your solutions and we will go through it again after the holiday. But this is number 6. So please solve this problem. This is a fixed support which has 3 reactions: vertical, horizontal, and moment reaction, moment resistance. That will be difficult if you haven't done this before. Same thing here. So this is a fixed support with 3 reactions: vertical, horizontal, and moment reaction. And there is no support here. So this end is free to move. So this is number 7. And as I said, do not worry if you haven't done it before, we will go over it again. But make a note so we know exactly where the problem might be. This is number 8, with a fixed support, free. This end is free and free, not supported. And this end here is fixed. So at a fixed end, you have vertical reaction, you have horizontal reaction, can be 0, but also you have moment reaction. I'm sorry about the quality of the sketching because I'm trying to write on the screen, so the quality is not very good. But anyway, so this is number 8. And this is number 9, again. A fixed end, a free end. So a free end, there are no reactions, only 3 reactions developing at the fixed end. You cannot have any vertical resistance here or horizontal resistance. No, that is wrong. because this end is free. There is no restraint. There is no restraint. And when you apply the load, the system will bend like this. Yeah. So it will move like this. So that's number 9. You have done this already for me, which you did very well, some of you, but maybe not all of you are confident yet. So thank you very much for you who did it based on the fundamental physics kind of course you've done. So it's number 10. But again, please do it again and hand your solutions completely to Professor Ben. Number 11. So yeah, this system is going to be interesting when we look at internal forces. All of them are going to be very interesting. Sometimes you might even find it difficult, but we'll try to help you as much as we can. So again, intensity, 15 kilonewton per meter. So each meter has got 15, roller support, hinge support. And find the reaction. That's 11. And that is 12 again. You've done 12. Some of you did very well. So thank you very much with the limited knowledge from before. So you've got 12 questions to solve and hand the solution to Professor Ben. I think that's probably enough for you actually for now. So please hand over the solutions of these questions to Professor Ben. I think maybe I will take questions quickly and then I can end the session a little bit earlier because now we have a lot of work to do. So you can do that. And of course, also look at the textbook and look at other kind of questions if you like, and try to learn as much as you can and prepare as much as you can. So I think maybe it's sufficient for today to have given you a lot of kind of information which was maybe higher than what you have done before. So I will think I will stop here and I will leave you to do the homework, and I will just take questions if you have any questions. Please, do you have any questions?
Teacher, I want to ask that on the third question, we just have to calculate the reactions of all of them and just let the answer to Mr. Ben, right?
That's correct. Yeah, you understood correctly. So all these questions, make sure you calculate the reactions and hand them to Professor Ben. That's correct. Yeah, correct understanding. Thank you very much. Yeah,
Yes, thank you, sir.
thank you. Any other questions, please? Oh, okay. You want me to go back to share the screen? Okay, okay. And number 5, huh? Number 5 you want? Okay. So this one? Is okay? Say it again, please. Oh, wonderful. Thank you. This one, 6? Yeah, 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 yeah. 11, and there's 12 as well. And that's enough for now, I think. But previously as well, I mean, you just asked for you have 5. You have 5 already, and yeah, okay. Maybe go right from the beginning, but that's easy. But you can also take this down if you like. This is one, very easy. This is number 2, very easy. 3 and 4. Okay, and then you already have 5. Okay, thank you very much. So, any other question, please? Any other question? No? Okay. So, if you don't have any questions, we'll end the session a bit earlier because now we have work to do. You can continue working if you like. I'm also not feeling very well. So, a little bit earlier. So, and also we need to start explaining things in detail from the after you come back from holiday. So what I'd like to do now is to wish you all a wonderful holiday and happy New Year. I think it's the year of the snake. So happy New Year and all the best for the holidays. And I will see you all after you come back from your holidays. Okay. Thank you very much. Thank you. Okay.
Thank you, teacher, and hope you have the nice holiday.
Thank you very much indeed. Thank you. Thank you very much. You too. Chat box, messages in the chat box. Thank you very much. Thank you very much.